Today we are going to talk about the next section, section 6.3, called Calculating Probability. Okay, so the first thing to note is when experiments have outcomes that are all equally likely, it is simple to compute probabilities. If S is the total sample space, so that's all possible outcomes, and E is one particular event, which is some collection of possible outcomes, maybe not all of them, some number of the possible outcomes, then to find the probability of the event, you simply take the number of things in the event and divide by the number of total things in the sample size. This is the number of outcomes in the event divided by the number of total outcomes. Okay? Let me give an example of when you would use this principle and when you would not use this principle. Okay? An example of when we would use it is you would calculate probability of rolling an even number on a six-sided die. Okay, that's how you can tell I'm a little bit of a nerd. I specify six-sided dice as if that's not automatic. Right? Some people know what I'm talking about. All right, so we have a six-sided die, and what's the probability of rolling an even number? Well, the event even is rolling a 2, 4, or 6. The total sample space is rolling 1, 2, 3, 4, 5, or 6. The number of things in the event is 3. The number of things in the sample space is 6. 3/6 is the probability, which we would often refer to as 1/2. Okay, so that's an example where when all of the outcomes are equally likely, this is how we can compute probabilities. A non-example is probability of rolling a 6 as the sum of two dice. Okay? We can't look at just the fact that we're getting a 6. We can't say, okay, well, the event is getting a 6 and the sample space is 1, 2, so I can't get to 1, right? We got 2, 3, 4, all the way to 12. And we would say 1 over 11 because there's 11 things in the sample space and 1 thing in the event. That's not correct. That's not correct. Because rolling all outcomes of the sum are not equally likely, right? We know that the 7 is the most likely one and that a 2 and a 12 are both tied for least likely. So in this instance, the outcomes we're recording the sum on the dice. And since all of those outcomes are not equally likely, we can't use this principle to compute the probabilities for that example. Okay, let's do another few examples here before we talk about the other rule for today. Okay, first example. A professor is randomly choosing a group of 3 students for a presentation. In a class of 10, 2 are on the debate team. What are the chances one is chosen, at least one is chosen for the group. Okay. So this is now we see why we did the last chapter first, right? We need the total possible groups that could be chosen. There are 10 students, and we are choosing 3 for the group. And of course, once they are chosen, right, the order does not matter. So this is a combination, not a permutation. And this is 10 times 9 times 8 divided by 3 times 2 times 1. And this is equal to 120. Okay. Now we want to ask, okay, how many total groups have at least one person who's on the debate team? I think it's an easier question to answer is how many groups are possible without a person on the debate team? Without a person on the debate team. Okay, how many people are not on the debate team in this class? 8 people are not on the debate team in this class. And how many are we choosing? We're choosing 3. So the total number of groups possible with nobody from the debate team is combination 8, 3, which is 8 times 7 times 6 divided by 3 times 2 times 1. That equals 56. Okay, now we need to say groups with a debate team person. The total number of groups is 120. The number without a debate person is 56. And so when we subtract, we get 64. So there are 64 groups with a debate team member on them. So the probability of a debate team person on a group is going to be the number of elementary outcomes of groups with the person from the debate team divided by the total number of groups. And then when we reduce this reduces to 8/15, and this is around 0.53. So it's more likely than not that someone will be chosen from the debate team on the group, which might seem slightly counterintuitive, but here we are. Any questions about how I computed this problem? Okay, these are a little bit tricky. These are not easy. Okay. Here's another example. Suppose a ship has 600 passengers and 4 have a rare disease. If they randomly screen 20 passengers, what is the probability the disease will escape detection? Okay, there's only 4 people that have the disease of those 600, and we are going to randomly screen 20 passengers. Now, the total number of ways we can randomly screen 20 passengers is combination 600, 20. All right, that's the number of possible ways we could screen. Those are the possible number of ways we could randomly choose 20 people from 600. And then if we how many ways in which we do this will the virus escape detection? It will escape detection if we choose one of those 596 people who are not infected. So the numerator here, the number of things in the event, is combination 59620. Now, using a calculator and figuring this out, this is about 0.87. So it's pretty likely that these 4 sick people will escape detection. Okay. The next rule is the complement rule. It says, let E be any event and E prime its complement. So E has a number of outcomes in it. E prime has all of the other outcomes. All of the other outcomes. That's what we mean by complement. Then the principle, which is pretty easy to figure out if you think about it, the probability of the event E is equal to 1 minus the probability of the event E prime. The probability of an event E is equal to 1 minus the probability of an event E prime. The complement event and the event itself have to add up to be 1. And this is often useful for finding some complicated things that it's sometimes easier to find the probability of the complement than it is to find the probability of the event you're looking for. That's what this is useful for. And so for the example for this, it's a very special example, which maybe you've heard of, is the birthday party problem, or the birthday problem. Has anyone seen this before, the birthday problem? No? Okay. So the question is, in a group of 30 people, what is the probability that at least 2 will share the same birthday? Okay, there's 365 days in the year. Okay, imagine we have executed all people with a birthday on leap day. So we're going to eliminate that possibility. There's 365 days in a year. What is the probability that at least 2 people will share the same birthday if there's 30 people in the room? You might say that's pretty low, right? Because there's so many days are possible, and there's only 30 people in the room. Okay. So let's think about this. Okay. The way we answer this is E is going to be the event 2 people, at least 2 people share a birthday. And E prime is going to be then the event of all people have distinct birthdays. So E is more than 2 people sharing the same birthday, and E prime is all people having distinct birthdays. Okay, E prime is going to be what we're going to focus on because this is somewhat easier to calculate. Let's assume that there are 2 people in the room. How many different ways can 2 people not have the same birthday? If we have one person in the room, then the next person comes in. How many ways are there for that person to not have the same birthday?
364.
Exactly, 364. So we get 364. And then how many total birthdays are possible for that second person? 365. Okay, 364 divided by 365 is a pretty small number. Let's see if I can actually do some amazing split screen stuff here. Like I actually know what I'm doing here. Okay, so let's calculate this. 364 divided by 365. Okay, so this is 99.7, or for probability, of course, it's 0.997. Okay, and so then here, the probability of E would be 1 minus 0.997, and that's 0.003. So roughly 3/100ths, right? Okay, yeah, that seems about right. Okay, that's not very likely at all. Okay, now let's take this baseline probability, this 364 over 365. Okay, let's assume that the two people in the room don't have the same birthday. Now let's let a third person come into the room. How many ways are there for the third person to have a different birthday from the other two? That would be 363 ways. Right? Because they can't have the first person's birthday and they can't have the second person's birthday, and we're assuming that those two birthdays are distinct. How many total birthdays could the second person have? That would be 365. Possible. So this probability is going to be 364 times 363. Divided by 365 squared. Okay, this is about 0.991, or so let's say 0.992. And so the probability of the event we're looking for, having two people have the same birthday, is still relatively small, 0.008, thereabouts. Okay. So now let's see, we keep having more and more people come into the room until we get 30 people. So this is 3 people. 30 people. When that happens, the probability is going to be 364 times 363 all the way down to, at this point, 333. No. Not quite, right? Let me think about this. Okay. With 2 people, it's 365 minus 1. So with 30 people, it should be 365 minus 19, which would be 336. Minus 29, not minus 19. And then in the denominator, we're going to have 365 to the 29th power. Right? Because with 2 people, we had 365 to the first power. With 3 people, we had 365 squared. So now with 30 people, we're going to have 365 to the 29th power. If you were to calculate this, you get 0.294. This is the probability that 2 people don't share a birthday. The probability that we're looking for that 2 people do share a birthday is 1 minus this probability. And that's going to be 0.706. So when there's 30 people in a room, it's 70% likely that 2 people will share a birthday. This seems very counterintuitive, but it is true. So, let's see. I think Wolfram Alpha knows about the birthday party problem. Or a birthday problem. Okay, and we give them a number of people. Birthday problem 30. We hit go, and it gives you exactly this probability that we are very close. At least 2 is the same as 0.706. Yeah, that's what we got there. Okay. So how many people are in here, right? Let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Wait, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 24. So there's 24 of us. So let's see what the party problem says about 24 of us. Okay, it's about a 0.53, so it's more likely than not that 2 people in this room share the same birthday. Does that seem strange? It seems strange, right? Okay, let's see. What do I got here? I got a $1 bill. Does anyone want to wager with me? Either way, does anyone want to? You're good. You got $1? Yeah. Okay. So what are you going to pick? Are you going to pick birthday? 2 people share a birthday, or 2 people don't share a birthday?
Don't share.
You're going to take don't share. Okay. All right. So we are going to. So I'm going to start, and we'll announce our birthday. You don't have to say the year, obviously, but just announce your birthday, and we'll see. It's apparently 53% likely, so it's close to even odds here, right? So Jake's betting on his intuition, and I'm betting on mathematics. So let's see who wins. My birthday is October 1st.
December 28th.
December 28th?
October 2nd.
October 2nd. Ooh, that was a close one. Jake's getting a little nervous right now. Travis?
September 4th.
September 4th. And if it matches your birthday, say it so we don't have to keep going, right? Okay. Audrey?
August 2nd.
Okay.
September 11th.
September 11th.
September 9th.
October
October 20th.
20th. Okay.
May 4th.
May 4th.
November 12th.
November 12th. March 10th.
May 30th.
May 30th.
March 9th. April 12th.
August 26th.
That's me.
Oh!
Good day.
How about that?
Good day.
That's weird. That is weird. Oh man, that's fun. Okay, you know what? I'll let
No,
you
take it back. It's a bet. It's a bet.
Okay. So now that you guys are allowed to congregate in large groups, you can make a lot of money on the weekend now, right? Are you ever in a room with more than 30 people? Probably. Right? Now, I mean, once you get to like 100 people are going to get a little suspicious, right? But yeah, this is a weird thing. Okay, this is a counterintuitive resultant probability. There's lots of them. Has anyone heard of the Monty Hall problem? Okay, we'll talk about that another day. Okay, so let me write down what the, let's see. The homework is going to be, this is section 6.3. 6.3. In class, I want you to work on number 2. We don't have a lot of time here. And then in general, for the homework, let's work on 6, 10, 12, 18, 22, and 24. All right.